Hello everyone. Welcome to YouTube channel Energy-Exergy Theory Applications. I am Tatiana Morosuk and I am author of this channel. Today we are with the lectures on engineering thermodynamics. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more. We will be happy to answer your questions and provide with extended information. Please find our contact email in the description of this video. Lecture 2 on engineering thermodynamics. Now we will discuss the first law of thermodynamics and concept of energy. I will ask you, when people discuss about mathematical models, what do you think in this moment? Mathematical model of the system, mathematical model of the process, always for us is associated with quite complex equations, sometimes partial derivatives equations or integral equations, and everything creates imagination of very high level of research, and we need time to understand all these equations and follow these equations. In fact, all mathematical models, regardless how complex are these models, it is set of balances. Very simple set of balances, or maybe balances with the properties of working fluids. But now we will exclude the topic of working fluids. We will discuss only balances. So one more time, all complex mathematical models, it is set of balances. And all balances written in thermodynamics, of course, in engineering thermodynamics, always based on the general scheme or general equation for all balances. Change in parameter, it is transport of parameter or generation and or destruction. All four terms together never will exist in any of equations. Always one term or two terms or even three terms can be vanished from this equation. But definitely there is no fifth term that should be considered. So every time when we have new kind of analysis, first we need to write balance and which terms should be considered in this balance. For example, mass balance. Transport is 0, generation 0, destruction 0. So change will be equal to 0. This is how a general balance equation can be reformulated for mass balance as a particular case. And we will proceed with examples, of course. So mass balance we will discuss for open system, for closed system, and for isolated system. Definitely mass cannot be generated and mass cannot be lost. Okay, mass can be accumulated, but it is already a different discussion, because here where, as you can see, delta m, it is not m dot, so we are not discussing about mass flow rate, we are discussing about total mass. At total mass in should be equal out. For closed and isolated system, mass is constant, because mass always will be inside of boundary conditions. Matter cannot cross the system boundary, that's why mass always will be constant. And for open system, we will write that sum of mass that is incoming to the system and sum of mass outgoing from the system equal to each other. One more time, I repeat, it is the total mass, it is not mass flow rate. But if we discuss about mass flow rate, I believe many people can remember this task from mathematics regarding the swimming pool, when through one pipe water is coming to swimming pool and through other pipe water is going out from the swimming pool. In this, for this example, of course, total mass will be constant. But mass flow rate incoming water and outgoing water definitely will be different, because part of mass will be accumulated inside of swimming pool. So therefore, one more time, I would like to pay attention that when we discuss about mass balance, here in general form, it is not mass flow rate. It can be the case that mass flow rate will be equal to each other, so I mean incoming and outgoing, but that will be a particular case that we will explicitly mention for each kind of evaluation, for each particular case as example. The first law of thermodynamics. For all of us, the first law of thermodynamics associates with principle of energy conservation. So there is no other definition of the first law of thermodynamics except principle of conservation of energy. And energy is a fundamental concept of thermodynamics, of course, and the most significant aspect for engineering thermodynamics and any kind of engineering analysis. So we know through this definition, we know that energy can be stored within the system, can be transferred from one system to another system or from system to surroundings, and can be also transformed from one form to another form. Energy cannot be lost and cannot be generated according to the definition of the principle of energy conservation. And energy balances, together with mass balances, it is the beginning of all mathematical models of the system. So always for the simulation, we need to start with mass balances and with energy balances. In engineering terminology, sometimes it's called engineering slangs, we use terms that in general contradict to the first law of thermodynamics. I mean, from theory point of view. We can say electrical generator. What means electrical generator? In fact, it is conversion of mechanical energy to electrical energy. Electricity of heat generation. It is conversion of any form of energy to electrical energy or to heat. And energy or heat losses, this is the most misleading term. In fact, it is transfer of energy, thermal energy, from a system to surrounding. This is very important for us. So transfer of energy directly from system to surrounding associated for us with the losses of energy. Let us return to concept of energy. Principle of energy conservation in general was already known since hundreds of years in mechanics. We know that kinetic energy always can be converted in potential, potential can be converted in kinetics, and together sum of kinetics and potential energy, it is the total energy of the system, mechanical system. And now we're discussing about thermodynamics in the first law of thermodynamics. What is the difference between energy, principle of energy conservation in mechanics and in thermodynamics? It is the term of internal energy. So for mechanics, one more time, I repeat, we have kinetic energy and potential energy. For thermodynamics, we have internal energy, kinetic energy, and potential energy. Equation to calculate kinetic energy and potential energy for thermodynamics and for mechanics is absolutely the same. And internal energy, we have just one new nomenclature and new term, U, internal energy, and we need to discuss what it means. Energy is definitely extensive properties of the system because energy, so amount of energy in numbers, definitely depends on the size of the system. Therefore, we always can rewrite total energy as mass of the system and internal specific energy as sum of internal energy, specific kinetic energy, and specific potential energy. Absolutely the same, using the same approach, we can rewrite energy not on mass base, on molar base, on volume base. Everything is possible. So all three possibility to express total energy as specific and corresponding size of the system always possible. So now what is the new in modern engineering thermodynamics? At present, no one is using letter E to describe energy because energy anyway consists of three parts in thermodynamics. Therefore, no need to use this one letter as description of energy. And actually now letter E is already reserved for exergy analysis. So this we will discuss later. So, and in modern thermodynamics, I will repeat, equation is written like that. Energy, there is no special term for that, and it will be only sum of three terms: internal energy, kinetic energy, and potential energy. So energy balance, for example, if we need to consider the transfer of system from state 1 to state 2, finally will be written like that: change in internal energy between state 2 and state 1, change in kinetic energy in state between state 2 and state 1, and change in potential energy between state 2 and state 1. And then change in energy, it is only transport of energy to change from state 1 to state 2. Now we have a question. How can we feel that energy transferred to the system or transferred from the system? Does not matter to another system or to surrounding. How we can observe it, how we can feel it. Our observation, it is work and heat. So if work done by system or on system, if heat is transferred to the system or from the system, it means that energy will be changing. So system will change from state 1 to state 2. So I will repeat, the change in all three kinds of energy or only in one, this is also possible, it will be expressed through heat and or work or together. Now energy balances can be written also, for example, in differential form. And now we can immediately observe that for energy we will use total differentials, and for heat and for work we will use partial differential. It is not a typo. It is there is some meaning and mathematical also meaning behind that. Energy, it is state of the system. State 1, state 2, energy for state 1, for state 2. It means that it will be total differential. Heat and work depends on the path. We can using even mechanics as an analogy, to walk from state 1 to state 2, we can go straight, we can use any of passes, and finally from state 1 we will reach state 2. But since we have many passes with many options, it will be partial differential for heat and for work, because depends on the path, can be different combination of these two terms. So one more time, it is not typo. Please pay attention. It is absolute strict mathematical rules. And also energy can be energy balance can be rewritten on time rate. So depends on the time. Change of internal energy by time, kinetic energy by time, and potential energy per unit of time. It's called on time rate basis. And then we have, instead of heat and work, we have heat rate and we have power. So we never will say work rate, it is power. Heat rate and power. And in thermodynamics, we have, of course, definition of work and definition of heat. Definition of work mainly came from mechanics. This definition is not very clear for thermodynamics because thermodynamic processes are not included here. And okay, I will read official definition of work that you can find in all books in thermodynamics, that work is done by system to its surrounding. It means that work is produced by system. We can observe it if the only effect that can be done external to our system that produces the work, it is the raising of a weight. Because in general, raising of the weight, it is something which is opposite to gravitation. So we need to overcome gravitation. It means that energy should be supplied to overcome the gravitation. And this supplied energy, it is work. So as I already mentioned, it is not clear from thermodynamic point of view, but it is classical definition of work. And the first equation, it is observable force and some hypothetical change in displacement. This is a definition of work, and work per unit of time, it is power. So the unit of work as energy, it is joule, and power, it is joule per unit of time per second, it is watt. Definition of heat is very simple. Everything which is not work, it is heat. This definition is very clear, and students like very much this definition. We don't need to discuss something which is quite difficult from thermodynamic point of view to understand as definition of work. So if it is not work, it is heat. And energy transfer by heat, always associated with change in the temperature. So if temperature of system will increase, it means that heat is supplied to the system. If heat is removed from the system, then definitely temperature should decrease. So this is our observation of energy transfer by heat to the system and from the system. And similar to work, of course, heat rate, it is joule per second, it is watts, and just heat as a form of energy, thermal energy, unit is joule. And now energy balance for the open system. Let us start with open system as a simple case. So mass balance, sum of mass flow rates coming to the system equal all mass flow rates going out of the system. Mass balance, sum of mass in is equal sum of mass out. And energy balance for the open system, we remember that not only energy can cross system boundary, but also matter can cross system boundary, will be written like that. So total energy, CV, it means control volume, it is, or open system, it is the same. It is heat transfer, work transfer, and sum of energy transfer to the system associated with mass flow rate. So it means specific internal energy, specific kinetic energy, and specific potential energy, minus also total energy transferred from the system, which is associated with mass flow rate. So mass flow rate that is going out, so that will cross system boundary from the system to surrounding or to other system. It is again specific internal energy, specific kinetic energy, and specific potential energy. So one more time, it is energy balance for the open system. This energy balance, mass balance, and energy balance for open systems, this is our particular case simulation of each component of energy conversion system, when each component will be separated from the system to simulate and further to evaluate. Our next lecture will be already dedicated to thermodynamic cycles and definitely efficiency, energy efficiency for cycles. So please give a like to this video, subscribe our channel, and share this video with your colleagues. Thank you.